understanding the number of samples you have to take in certain lots. If you make 10,000 products, 10,000 chips, how many of those do you need to sample and then actually see what the mean is to have a certain level of confidence about how the thing's working. It's very, very important that you appreciate how this stuff really applies in the real world, because it's the difference between making or losing money. So right now for the quiz, let me go over that. And I noticed with the EMAG class, he's making you calculate the number of modes in fiber optic.
It's like the only thing that we have to calculate.
How many know something about fiber optic? Anybody? What is the one singular thing that they have in almost all fiber optic cables for telecommunications? Anything? One mode.
Yeah.
It's not multi-mode. Multi-mode is something they use a graded index usually on a fiber. And I'm just saying this, if you're not any man, don't worry about it, but single mode fiber requires a very small intercore. And it is glass basically, so it has all sorts of limits on how much you can bend it. But that's material science and materials engineering, not really electrical. He doesn't do cylindrical modes, does he? Just rectangular modes for waveguide? Mm-hmm. Cylindrical are interesting, and that's what you need to do to understand fiber optic really well. Anyway, back to this. For the first problem, I think this is the quiz. And it said, I think I had an f of x equal to 2e to the minus 2x u of x is the first probability density function. And the second probability function I just said is uniform from 0 to 2. So I'll call this f of x of x. I'll call this f of y. And this one is just between 0 and 2, which means it has to have a height of 1/2. And I'm not saying anything here that's revolutionary. Now, when you're doing convolution, and some of you have, I think, just stumbled with the convolution thing. You understand, for this, if I have a variable, z is equal to x plus y. And if you go and look in the book, and if you wanted to think about this, you can actually say y itself, I'm going to just mention this, y itself would be equal to x minus z. And if you took a look at this is x and this is y, you get this kind of a idea. This would be for a certain value of z right here. And we take a look at the probability that, if you want the probability of this, what you're really saying is pick a value for that. You're saying, what's the probability that x and y will be in that region? That's the idea. So when you go through this thing and do it, set it up, what you're going to end up getting is going to be two integrals. And one of the integrals goes from minus infinity to x minus z, and the other integral goes from minus infinity to infinity. You all follow me on that? And the dummy variable here would be, if it's either going to be x or it's going to be y, one of the others, and you're going to integrate it out, and it turns into a convolution interval. If it's this, if z is equal to x plus y, if z was equal to x minus y, then it's correlation. But I'll show you a trick with that one. I mean, does everybody understand this results in a convolution integral? Everybody? All right, so I'm just going to do it. Given that, the way when I teach this stuff, I try to tell people, when you're doing convolution of any two functions, I'm going to write it this way. I'm going to say my f, this is my insurance company. Yeah, I'm turning it off. It's Scott Hall. Don't worry about it. Anyway. For this, my f of, and I'll call it fz of t for now, is just going to be the convolution of x of t convolved with fy of t. Some people, I think, still have problems understanding that at the end of the day, I'm going to take that t and just replace it with a z. But when you're doing convolution, at the end of the day, the dummy variable is gonna integrate out, and you're gonna be left with what it is a function of. It's a function of z. So here, since these are convolutions, I'll write down what this is. Mathematically stated, is going to be the integral from minus infinity to infinity. Technically, it's that level. And then it's going to be f of x, and I'm going to leave this as the dummy variable of tau times f y of t minus tau d tau. Now tau there is the dummy variable. It doesn't matter what the value is. I mean, what symbol you use. The t is what the function of this is, and we'll replace it by z at the end. Okay, when you're doing this, one of these functions is just going to be a function of tau. You're not going to flip or shift it. And I always tell people that when you're doing this, it's best to take the function that has the most change to actually, and graph that and leave it alone. So I'm going to use this one because this is a straight exponential. It's got a whole lot more change than this. Okay? So now I'm going to put f of x here of just tau, and that's this. And it's really 2e to the minus 2 tau for tau greater than 0. Now below it, the next thing I do, it's versus tau, I take this function and I flip it. So when I flip it, I get this, and it would be at minus 2. Is everybody with me on that? Now I shift it. Now if this here, if you think about it, when I flipped it, this is still 0. This is going to be whatever this is minus 2. Y'all follow me? Now when I add the argument of t in here, what I'm showing you right there is fy of tau. Then I'll get this. This would be my fy of t minus tau. And a lot of you know how to do this, but so this point would be t, this would be t minus 2. Everybody with me? And the height on this is 1/2, by the way. It's easy to miss that because it is a density function. Now, you take a look at this boxcar as t increases. If you look at this when at 0, when t is 0, there's no overlapping area. In other words, when we're going to multiply this by that function, and it's the overlapping area that we're going to integrate. Basically, we're going to find the areas. Well, for this one, as it's moving through, this would be for t greater than 0, less than, and it would be 2 right here. What you're going to get is this is the overlapping area. So I would multiply this function by this function and integrate it. Do y'all follow me on this? I think everybody, you've had signals and systems, you know how to do convolution, but sometimes you don't use it enough. So for that one, you can do this problem, by the way, with Laplace transforms. But the problem is this function right here, the boxcar, is going to be what you call a rect function. And the Fourier transform of a rect function is a sinc function. And it's a little more difficult because a sinc function times an exponential, the integration itself, when you do that thing, it results in something that's very hard to go in the opposite direction, get it back to the actual time domain. And as this one's simple, it's going to be, this is just 2 over 2 plus s. But for this function, the boxcar thing, it's tougher. It's really 2 pulse functions. Or I should say 2 u of t functions, but that you mess with. Getting back to this thing, when I'm going to do this, the overlap area, I'm going to say for z greater than 0, less than 2, or really, I'll make it t. I'll make z at the end of it. My value for f z of t would be equal to the integral from 0 to t of 2, but it's going to be multiplied by 1/2, so it's 2 times 1/2, so it's just 1, and then it's e to the minus 2t per tau, 2 tau d tau. And that means my fz of t here is just going to be equal to 1/2. It would be 1 minus e to the minus 2t. I'll leave it like that. That would be for t greater than 0, less than 2. Then, as time goes by, when t gets greater than 2, there were a lot of people made mistakes on this, and I wasn't absolutely sure what the problem was. But now, if this is t minus 2, and this is t, this is for t greater than 2, still would have 1/2. Now the overlapped area is really here. And so for that one, fz of t would be equal to an integral from t minus 2 to t of e to the minus 2 tau d tau. By the way, same kernel of integration, only the limits change. That will be true on all these where you have an exponential. It's just, for z or for t or z greater than 0, it exists. And you got some other function that's got a limited time domain, or a limited time slot that's moving. And this doesn't have to be something that's a box plot. It could be a triangle, it could be anything. Y'all follow me on this? You have to make sure you do the math carefully on those. And this one is going to be equal to, here I'm going to get 1/2, and then I'm going to get e to the minus 2t minus 2 minus e to the minus 2t, and then factor out e to the minus 2t, so I get 1/2 e to the minus 2t, and here I'm going to get e to the 4th minus 1, and finally, and this is for t greater than 2, less than infinity, or greater than or equal to, doesn't really matter. And then the last thing you can just say is replace the fz of z just is equal to 1/2 times 1 minus e to the minus 2z u of z. And this is going to be for z between 0 and 2, and then between 2 and infinity, f of z is just going to be equal to 1/2 e to the minus 2t times e to the 4th minus 1. Okay, simple. That's the first part. Second part, I gave you a different function, right? And are there any questions about this? I literally took a homework problem and I changed one thing. That was it. Do you all recognize that problem, by the way?
Yeah, it's the boxcar one just with the exponential, right?
Yeah, but we did this in class too, I believe. All right, next problem, or the next part of the quiz, was part B. Now I still have my f of x is 2e to the minus 2x u of x, but now got a new function, it's g, or capital G. I just put f of g here. F of g of g, and that is equal to, 4, is it? All right, 4 e to the minus 4 g u of g. Did y'all agree with that? Now this one, you can do it by the flip and shift method. It's a little aggravating. But remember what I told you on these things? What was the easy way to do it? I'll do it the easy way, then I'll flip and shift.
With the transforms, right?
Yeah, I mean, so you know that if you've got convolution in one domain, I'm gonna just replace this and say when I take a look at this, I have a function, I think I called it u is equal to x plus g, right? And now I wanted f of u. You can call it, or it doesn't matter, you can call it z if you want, doesn't matter at this point. You all agree with this class? It's a function of this. But if you want this, you can say, well, if I have convolution of f of x of t convolved with f of g of t, now I'm replacing these variables with the t variable because it's going to be a convolution to get that answer, my f of u, which would be of t, but then we'll replace t by u. I can go ahead and get the transforms, and that would be f of x of s times f of g of s. And when I do that, transform of this one is 2 over 2 plus s. It's times transform of this one is 4 over 4 plus s, or s plus 4, doesn't matter. Did anybody do it this way in this class here? You did the flip and shift one? I believe I did this problem on the board too for a reason, because I wanted to make sure you understood how to do it this way, because it's very easy to do it this way. And then that breaks down to two, you basically do partial fraction expansion. There's simple poles for Greek class. And because there's simple poles, it becomes a over s plus 2 plus b over s plus 4. Now you got to solve for a and b, right? Remember how to solve for them? Here, yeah, give you a bit. Or not.
It was you.
I call it the cover-up method, right?
Mhm.
Look at where the first pole turns on. It's at s equals minus 2, right? So go over here and multiply. Well, what you do is multiply everything by s plus 2, and then evaluate that at s equals minus 2. All right, when you multiply by s plus 2, that pole goes away. Then when you multiply this by s plus 2 and evaluate it at s equals minus 2, you get 0 times this. That goes away. And you multiply this plus s plus 2, you get rid of that. And when you evaluate it at s equals minus 2, you get 8 over 2, right? And 8 over 2 is 4, correct, class? So I know this is 4. And then to get b, you do the same thing all over again. You're going to find out for simple poles like this, b is going to be minus the first, the value. This one is it'll be a minus 4. So I multiply everything by s plus 4, and then I evaluate it s equals minus 4. So I get 8 over 2 minus 4, or minus 2, and that means this one is minus 4 over here. Agree? It's straightforward, I promise you. Now I take this and I go back the other way. So I know that when I take these two and I transform this way, this one becomes 4 times e to the minus 2, and it doesn't matter, that it's u, and it would be, that's the first one. That one is going to be minus 4 e to the minus 4 u, and they're only valid for u greater than 0, so I can call it u of u, even though that won't work mathematically. And that would be my, I'll call it f u of u. Y'all with me? Now that's with the poles. If you did the flip and shift method, and I guess this whole class did it, the flip and shift. It's a little more involved to do it, but it's doable. That one, you flip and shift. It really doesn't matter which one you flip and shift. So that's the first function. Then when I flip and shift the second function, I get this. And here, if I look at this, you can call this, I'll call it t, because when we're doing convolution, I like to use t and then replace it by whatever the variable is, z, u, doesn't matter. You agree, class, on this one? So here, you're going to have 4e to the minus 4, but then in here, it's going to be t minus tau. Do you agree with that? Agree? Now the integration will go from 0 to t, correct? All right, so here, the final thing would be my f of u of t would be equal to an integral from 0 to t of, and here you gotta do point, so multiply out, I get 8. Then I get e to the minus 2 tau. Well, I'll go ahead and write that. So I'm gonna have e to the minus 2 tau times that, which is going to be e to the minus 4t times e to the 4 tau d tau. Everybody agree with that? I mean, is this how you guys, when you did it, you have that basically? I'm making sure. Is that how you did yours? Or? I'm not sure. So I can take the e to the minus 4t out in front, and then when I do it, I get, and I can take the 8 out in front, and I get e to the 2 tau, and integrate that, and that's going to be 1/2. Then I get e to the 2 tau evaluated from 0 to t, and that's going to be 4e to the minus 4t. And here you're going to have divided by, then you're going to have second. That's 4. That isn't 8. Sorry. Yeah, this should be like that. And that would be equal to sorry, so that's going to be equal to 4 times e, and that would be a minus e to the minus 2t minus e to the minus 4t times u of t. And you can replace t by u, but the two things are the same. You agree with that, everyone? Okay, that was the quiz. And I guess everybody got 2, 4, 6, 7. Okay. Any questions about that? I'm going to level with you. It's a whole lot easier doing pole expansion. And they're simple poles. I'll not give you anything tricky. What's the Laplace transform of a delta function? Anyone? 1. Remember that? Mm-hmm. Delta t, 1. What's the Laplace transform of u of t? 1 over s, right? Do y'all remember that? What's the Laplace transform of any exponential? It's always going to be, if it's e to the at u of t, it's e to the minus at u of t. It's going to be equal to simply 1 over s plus a, you know? And that would be, those are the transforms you should know for any of this stuff, anytime, because It's so much easier to do that with pole expansion. That's the real point I was making. And I want you to be able to appreciate that.
Okay.
Next. Now we're into chapter, we're doing chapter 4 in the book. And I put a new solutions manual in this morning that is much clearer. And it's the entire solutions, and it has all the solutions in the textbook. Well, I should say just about all. A few that they omit, but just about all. So for this, what I wanted to do is the next stuff. Is talk about here's the way I'm going to do it. Because I'm going to talk about exercise 4-3.1, and then we can do at least one problem in the 4-3 section, but I want to get into section 4-4 today too. So here's exercise 4.3.1. Just give me your attention here. I know you got a test coming up. Try to follow me on this one. So this is an exercise 4-3.1. And for this one, what did they, or what is the statement of the problem?
For the random waveform of figure 4-1.
All right, here's the one. For 4-1, it has a mean of 10 and a standard deviation of 9. If you're reading this exercise, you have to understand, if you just look at 4-3, the figure that they're referencing doesn't have that information. It's in the actual paragraphs below there. But go ahead.
Find the sample size that would be required to estimate the true variance of the waveform with a variance of 1% of the true variance if an unbiased estimator is used.
All right, so what they're saying, the variance of this is going to be 1% of the true variance. That's 0.01 of 9. Y'all with me on this, class? Now what he really is saying, and I wish he would say it a little clearer, he says he wants the variance of the samples. With me? Because this is when you have samples, you're going to have a mean, and then you're going to have the variance of those samples. You with me? And if you look at this, the variance of the samples, sample variance, that's what this is, the variance of the samples variance. And he gives you this, because he gives you 9 as a standard deviation, that's the true variance, and he wants 1% of that, it's 0.01 times that, with me? That's how accurate he wants this, the variance of the samples variance. And what is that? Some of you remember, but it's what? N over n minus 1 squared, right? And then it's u to the 4th minus sigma to the 4th, right? Y'all remember? If you don't remember this well, this is a form you're going to have to know. Right? I mean, I'm not going to give that to you. You got to know that one. Now, there are two possibilities for u to the 4th. They can be a Gaussian u to the 4th, or they can be the uniform distribution that we'll talk about. The uniform is slightly different. If you remember that one, I gave it to you. We can actually prove that. But for this one, we've got to get u to the 4th for a Gaussian. So if you think about this, any of these central moments, remember we're taking the expected value of x minus x bar to the, right here to the 4th power. We want the mean of that. And that's the 1 times 3, because here n is 4, right? And then it's going to be times sigma to the 4th. So that's simply gonna be 3 times 9 to the 4th right here. Or really, you can call it is sigma, but this 3, I'll leave it as, tell you what, do this. I'll make this sigma to the 4th for a reason, and you're gonna see. Now, if you go over to that right here, or up to it here, now I get really 9 times 10 to the minus 2, that's on that side, is equal to n over n minus 1 squared. And here, u to the 4th is going to be 3 times sigma to the 4th minus sigma to the 4th is simply 2 times sigma to the 4th, or 2 times 9 squared. I'm going to stop and make sure everybody got you on this one. Everybody's with me. I just replaced the sigma to the 4th by 9 squared. 9 is sigma squared. If I square that, I get sigma to the 4th. Did anybody look at this exercise? This one will cause you to stumble. And he talks about unbiased and biased estimate. Don't worry about that. Either one is within a value of 1. Just trust me, I'm not going to worry about that on a test. All right, now the question is, what is n? And here's the way I'm going to do it. If I look at this, you don't have to do it this way. I'm going to divide everything by 9 for starters. You with me on this? Now take a look at this. Now I can go ahead and divide it by 10 to the minus 2. And that means just multiply by 100, right? And then go ahead and break it down. So I get n squared minus 2n plus 1 on that side. I'm multiplying both sides by n minus 1 squared is equal to, and here it's going to be equal to 1800 n. Agreed? Go ahead and take this to this side, so I get n squared minus 1802 n plus 1 equals 0. That is n equal to about 1801, I think. Can anybody solve that for me? Because you're going to get either 1801 or 1802 if you round. But I don't remember exactly what the exact value is, but you take it out in decimal points, you got to round things, what I'm getting at. You can't have 18012579 because that ain't a value of n. And it's integer. You have root solvers, right, on your calculators? Do they do higher order roots too? Like polynomials of order 4 or 5? They do?
1802.
1802? Either one is correct. You with me? When I see a number like this, I ignore the 1. Because 1 compared to that 1800 is insignificant. I just take that to the other side, you see. And it's going to be about 1802, 1801. With me? Somewhere in there. A little bit less because of that 1. That's it for that problem. I'll tell you though, when you're reading, if you just are cramming and you fly through those sections, he's going to have the variance itself, which he has as capital S with a tilde squared is equal to, and he'll show you calculations on that, the formal calculations calculating it. Well, I'm never going to ask you to calculate the sample variance for like 20 values. You should know how to do that because it's like calculating the variance for anything. First you need the mean value, right? Then you have to take the value of these things individually, x of I, minus that mean value. You have to square it, right? Then you have to sum it from over all values and divide that by 1 over n to get actual value. With me? The average. But I'm not gonna ask you to do that, but you should at least understand how to do that. All right, that's that. I want to talk about that, because I looked at that, and I know, looking back at some of the formulas in there, if you tried it, when he mentions biased and unbiased, you'll get confused, because you're trying to calculate an actual variance where you don't need to. I mean, you don't have to calculate that. So, okay. Now, the next problem I want to do, and I gave this to you for home. How many did 4-3.3? Did you do it? No.
Most of it from the test.
Even a test? Okay. I want to do this for everybody. And 4-3.3 is really, in my opinion, it exposes a lot of stuff. We can do 4-3.2, but I put those solutions, I put that solution up for sure. I want to do this one, and I also got a few other things I want to do. Can you, I'm not asking you to do a lot of this. You just happen to be conveniently located.
That's the random phasing.
Wait a second. 4-. Yeah. Now this one does not have a Gaussian distribution. You hear me on this? So we're going to talk about this. Go ahead.
It is desired to estimate the variance of a random phase angle that is uniformly distributed over a range of 2 pi. Find the number of independent samples that are required to estimate this variance with a standard deviation that is 5% of the true variance if an unbiased estimate is used.
All right. So we want the number of samples that are needed to estimate this. And what does it say about read that again about the accuracy?
Estimate this variance with a standard deviation that's 5% of the true variance.
So estimate the variance of the sample stuff. This S squared is the sample variance. And he says within 2%?
5%.
Of the true variance? Read that with the standard deviation, because I'm trying to get that.
Find the number of independent samples that are required to estimate this variance with a standard deviation that is 5% of the true variance if an unbiased estimate is used.
Okay. That sounds like it's the square root of this, the way it was stated. And it's 5% the true variance? So that's going to be that would be the way you would interpret that statement. Because if this is the true variance, S, the variance of S squared, then the standard deviation of that would be the square root of that. With me, class? So now I'll go ahead and square that. So I get really 5 times 10 to the minus 2 squared. And then it's going to be times sigma to the 4th. This is the nice one. Now over here, that's going to be the n over n minus 1 squared. And here, u to the 4th minus sigma to the 4th. But u to the 4th is not Gaussian. Now, u to the 4th is a central moment, though. You with me? And here's one trick I want to make sure I can tell you, everybody. If you look at this, this would have a height of 1 over 2 pi. And this would be my f of, you can call it theta, it really doesn't matter, f of theta here, because it's a phase angle. But because this is a central moment, you can shift this so it has a 0 mean. This does not have a 0 mean. Y'all follow me in this class? And because of this, you can go ahead and shift that and make this f of theta just extend from minus pi to pi. And I'm going to do that to make everything easier. And you can look at this. Make it back. Now, the mean is 0. And if we look at the value of the standard deviation of this one, just think about what that would be. we actually want the fourth central moment of this, right? So let me go ahead and say this. If I look at this, the fourth central moment of that function, and I'll call it theta. Really, I'm going to make a point here. Do you all agree because the mean is 0, the fourth central moment would be the fourth moment? Y'all follow me on that? You know what it do, basically. If you have a mean of 0, the fourth central moment, since it's a mean, it's just the fourth moment. So if you take a look at this, the fourth moment of this one, or u to the fourth, would be equal to an integral, and it would technically be from minus pi to pi of the density function, which is going to be 1 over 2 pi, times the value of this, and I'm going to use the symbol x because it's easier, x to the fourth, and it would be dx. Now, I want you to first understand what I'm doing here. That would be the fourth moment of that, but it's also this fourth central moment because x bar would be 0, or theta bar. It has an average value of 0. So you got to make sure everybody sees that. This one is what? Well, that's really equal to 2 times the integral from 0 to pi of 1 over 2 pi x to the fourth dx. And that's simply going to be 1 over pi. And then you integrate x to the fourth dx, you get 1 over 5. And there it's going to be x to the fifth from 0 to pi, or pi to the fifth. Let me stop for a second. Everybody understand? I put a 2 here simply because that's an even function. It's symmetric from minus pi to pi, right? So I can go ahead and just double the integral from 0 to pi. That's my point. Do y'all agree with that? And this is simply going to be 1. Well, that's going to be pi to the fourth over 5, and that would be the fourth central moment. So getting back to that thing, I'm going back here. Now that's the true sample mean. This, now I come back here, and I get 5 times 10 to the minus 2 squared sigma to the fourth is equal to n over n minus 1 squared u to the fourth, or pi to the fourth over 5 minus sigma to the fourth. Now I come over here, and I don't know if you remember this, but for this function, since we have this function here, the value of sigma squared for a uniform, for something that's got a uniform distribution is just delta x or squared over 12. We could prove that. Do you all remember that? You can actually prove that by just making this squared, doing the integration on that. You're going to find out that this has got a span of 2 pi, so we got 2 pi squared over 12, and that's 4 over 12 pi squared, or it's pi over 4, or pi squared over 4, and that's sigma squared. Now going back over here, let's see if those things can break down. Now I got 5 times 10 to the minus 2 squared. Sigma to the fourth is going to be pi to the fourth over 16 is equal to n over n minus 1 squared times pi to the fourth over 5 minus, and pi to the fourth over 16. And let's see, the pi to the 4 scope. So I have 5 times 10 to the minus 2 squared over 16 is equal to n over n minus 1 squared. And now I have, wait a second. This should be a 3, my bad. Divide both by 4, you get 1/3, my bad on that one. So this should be 9. That should be 9. And that makes this 9. And that makes 1/5 minus 1/9 here. I don't mess around. I'm going to go ahead at this point and see if I take a look at this. This is just going to be solving it mathematically. So I'm going to get, multiply everything by 9. 9/5 minus 1. And then after that, well, 9/5 minus 5/5 is 4/5. Trying to get this done quickly. So I have 4/5 here. And then if I take a look at this, this is really 25 divided by 10 to the 4th. You gotta understand, I'm just trying to get to this end answer because it's just a simple formula. And then at this point, let's see. Quick way to do this. Yeah, multiply by 10 to the 4th, divide by 25. Equal 1. Let's see. So you got 40,000 divided by 125. I'm not sure what that is, but at the end of the day, if I want to solve this one, multiply everything by n minus 1 squared, and then expand it. So I get n squared minus 2n plus 1 is equal to that. Now I get, can you give me what value this is? Because I can't do that in my head.
320.
320?
Yes, sir.
All right, so now I'm going to get n squared minus, and I'll just take this to that side, minus 322n plus 1 equals 0. Can you tell me the value for n for this one? You have root solvers, because it's going to be about 320, I think. Anybody? Is it 320 or 322?
I got, I think 322.
Is that right? So, I mean, you can solve this stuff, right? It's about, I'm just gonna say about 322. Anyway, y'all follow me on, the difference between that one and the one we did earlier was that ain't Gaussian, and you can't assume that you can use that u to the fourth as 1 times 3 times sigma to the fourth. Here, you have to either calculate it, and there are tables for that, but I just did the calculation. You with me? Now, if for whatever reason, hear me now, if I give you a waveform that isn't like that, it's different, you have to calculate. I'll probably always give you something that's got a mean zero, just to make life easier. But you would have to calculate what the force central moment is. With me on this, class? Just so we're clear, you would have to know how to calculate that. Okay, said that. Now, the next part, because we have a little time. Okay, I'm going to show just mention some things in a PowerPoint that he has, but this is going to be on confidence intervals. It's going to be on section 4-4. I want you to understand, so you don't have to take super notes. It's already, this is on the PowerPoint, Denny's PowerPoint, but it is important to understand what he's doing. I'll apply it to some problems. Hopefully we'll have time for these things today, because this stuff is pretty important. Nothing. Some right function. So, anything? Can you also, you don't need to turn the lights on. All right, in section 4.3, that was the section I did the problem on. The real thing is with that variance of the samples variance is equal to n over n minus 1 squared times u to the fourth minus sigma to the fourth. That sigma is the real true sigma of whatever the events are. Like, they had the density function over there. We can calculate the sigma squared for that, and the sigma, or really sigma squared. But the u to the fourth is the fourth central moment, and that's the thing that can throw you, because that density function it can be anything. You don't know for sure. All right, now we're into this next section, and this is about confidence intervals. So remember before, the variance of the mean, not the variance of the sample variance, but the variance of the mean of the samples was this. If we got a large, basically we're sampling something that's got an enormous number of samples. Follow me? And obviously it goes down as n goes up. Now, so he states something. Assume a waveform is being sampled. It's a random waveform with a true mean of 10 and a true variance of 9. Well, if you know that, the obvious question is, why are we even sampling? We've got the information. But we're going to work backwards. Once we get, and you're going to see this in a bit, we want to see how confident we're going to be in certain events. And you're going to see something here where we don't know either the variance or the true variance or true mean, but we'll be able to estimate both the variance of the variance and the true variance of the true mean by using something called a student t-distribution. Just bear with me on this one. So here's this question. How many samples do we need to estimate the mean within 2% of the true value of the mean? Well, for this one, obviously the variance here is going to be equal to 2%, or 2 times 10 to the minus 2 of the true mean, which is going to be 10. With me? That would be the problem, how I'd state the problem. And anyway, he goes, so 9 over n is going to be less than or equal to 0.4 equals n is 225. Basically, he's solving for n. Given this statement where he's going to have, that's the variance, then, I'm sorry, this is going to be 10% of the true mean. Then he's got to get the variance, he's got to square it over here. And here's, suppose we use 225 samples and compute the sample mean. Are we guaranteed that our value is within 2% of the true mean? No. And you got to understand something. We're now going to create statistics. We're going to assume some things, statistics that are going to be basically, we're going to get an actual probability density function for the sample's mean and variance. You're going to have to go with me on this. And he says, are we guaranteed? No, we're not. So what is the probability that the actual sample mean is within 2% of its true value? We need the probability density function of the sample's mean. All right, you got me on this one? So we're going to have a probability density function that the mean of the sample will be, basically going to get that density function. So here's what ends up happening here. I want you to listen on this one. In the case the sample is large, and the central limit theorem tells us that we can assume x is going to be Gaussian. Recall that in previous slides, if the mean is 10 and the variance there, basically you're going to get the variance of the sample mean is 0.04. And if you look at this, if that's 0.04, that's the variance, so standard deviation would be 0.2. With me? Now if you take a look at this, and what he does here, he's going to assume that he's going to use this normalized, do you remember when we did the density functions and we got rid of the mean value and the standard deviation? So now he's going to take this, and these are basically like the f of 10.2 minus f of 9.8, and he's saying this is 2% of its true value, this range, because if its true value is 10, then 2%, 1% would be 0.1, 2% would be 0.2. So he goes from 10.2 to 9.8. You all with me on that? Because the mean value is 10. And he wants to see what the actual probability is that's between those things. And it turns out to be 68.26%. Now that's 68.28 or 68 or 0.6826 would be something that we're going to liken to a confidence interval in a second. Just bear with me. So to answer the questions like this, we need to know the probability distribution of the sample mean, and the normalized sample mean is this. Now here is something you got to understand. For this one, Z here, he's assuming we know the true variance. You see that sigma? That indicates the true variance. But if we don't, now listen, if we don't know sigma here, and you notice it's divided by square root of n, if we don't know the true variance, then we can take the sample variance and divide it by square root of n. Remember, this downstairs is usually just sigma, but if you think about this, the variance of the samples, or of the sample mean, was equal to sigma squared over n. You recall that? So if you take the square root of that, you get sigma divided by the square root of n. That's what goes here, because it's always going to be a standard deviation you divide this by. And that's the standard deviation of the sample mean. That's what I'm saying. You can write that down if you want, but you'll see. And this is something called the student T distribution. It's got by a guy named Gossett that worked for, what you call Guinness, the beer manufacturer, Guinness Stout beer. And you'll see this. So now we get this X bar minus X. And as remember, this is going to be the stuff we plug into those cumulative density functions or the student T distribution function. That's divided by square root of n. You noticed here, one thing you're going to have to take a look at. We still have the true mean here. This is going to be the sample mean. This is kind of important, but the true mean itself will go away if we want to know how close we are, or what confidence interval we have that when we sample these, or that when we do these actual calculations, that we got 90% or 95% chance of the sample mean being within that range. Hang on. So for that, let me go ahead and get the PowerPoint of this. Where is that? Am I missing? All right. All right, now this one it says, well, sigma squared is known. Why am I doing this? This is the question I have. And the sample size is large, n greater than 30. That's basically a large sample for a lot of reasons that I can't get into right now. Or basically samples are Gaussian. The sample mean is Gaussian. And now you can say the variance of the sample mean will have this characteristic. And then you can normalize and get this value of z right here. Now, remember that x bar right there is unknown. Sorry, it is the true sample. So here's a problem. And it says if we have 100 bipolar transistors and we want the mean value of the current gain beta, and the true variance is the true mean is 120, and the true variance is 25, or I'm sorry, the sample variance is 25. What is the probability, and this really showcases what I'm trying to get at. It's a perfect example. What is the probability that the sample mean is between 119 and 121? Now, when you think about it, I'm going to go back a few slides. I'll get there. Remember this z argument here. That z argument gets placed right here and here. Y'all follow me on this? These are the cumulative distribution functions that are normalized. You always now your distribution function, you plug in the value of the standard deviation is 0.2, of the mean is 10, and then you would plug the upper value and the lower value. Follow me? You can do that on your calculators. So we're calculating the value of z that's going to go in there after these calculations right here. So I have 119. Remember, this is 25. The square root of that would be the sample's variance, or the sample standard deviation, which would be 5. But we have 100 bipolar transistors, so the square root of 100 is 10. So this is going to be 5 over 10, or 0.5. That's where that 0.5 came from. Now the upper limit, the mean value, the true mean, true mean is 120. So we have 119 minus 120 over 0.5 is going to be the lower limit, and the upper limit is going to be 121 minus 120, or really this is just minus 1 over 0.5, or minus 2 to plus 2 right here. So think of a Gaussian curve, if you will, and now you're going from minus 0.2 normalized to plus 0.2. And that's really going to be equal, what they're showing here. This is that function that has the normalization included in it. Or 2 times the value of this one minus 1. And you get a value of 0.9544, about 95% chance, based on the information above, you'll be within that range. The sample size is small. Now we use the student t distribution. That's this one. And you notice now we use the sample variance, not the variance, the actual the sample standard deviation, not the true standard deviation divided by square root of n. So it's the exact same formula, only replacing the true standard deviation with the sample standard deviation. All is said and done on this one. And this is basically how it all started. Again, it stopped. The guys, the reason it's called student's t distribution, I'm just going to tell you. It's a guy named, where is he? Did he mention Gossett? I think he does somewhere. Well, maybe he doesn't, but he does mention it somewhere here. Maybe I missed it. It's called student t distribution. The guy's name is Gossett that figured this out, and he couldn't publish. Guinness had a company policy. You can't publish with your real name, so he called it student, and it's called a t distribution now. I'm going to tell you that. I'm not going to test you on that. Kind of curious. It's very interesting how I figured this out too. So here's the student t distribution. You're taking a look at this and you're wondering, see, this is the density function of t. It would be like the density function for x or any variable. And it looks very much like a Gaussian. And as the value of the samples, number of samples goes higher and higher, it will become a Gaussian. This is called a gamma function, right there. Have you ever heard the term gamma function? It's not something you're exposed to usually at the undergrads. If you take a math course with any kind of advanced mathematical functions, you'll get gamma functions. It's very common. But what he's going to, I don't know if he even says this, V is the degrees of, N is the degrees of freedom of this thing. And he goes, this is a recursive relationship for the gamma function. And he just wants you to calculate. Don't worry, I'm not going to ask you to calculate these things. He wants you to just simply calculate that crazy distribution for a value of 1 with 4 degrees of freedom. You probably wonder, what are these degrees of freedom? And actually, I don't have a good answer for you, but I know what it has to do with a brewery process. And what they really want to do is find the probability when they sample these things, the alcohol level would be a certain value, because when you sell beer, I think it has to state the alcohol content, the percentage, like 4%, 5% alcohol. And so he's basically figuring out how many samples you have to take if you're making beer of this process in order to have certain confidence in it. And there's the table for student T. What does that have to do with it? Here it is. Gossett worked for Guinness Brewery and has strict policy against employees publishing under their own name. So he called it student T. And apparently Tom Denny likes Guinness stout or Guinness beer. Now, I'm not going to test you on student T, but I will test you on Gaussian sampling for large numbers, and I've got one problem. I don't think I have time to do it, though. This is the one thing you're going to have to realize. When you go through, remember how before you would have a value like x minus x bar over sigma? Y'all remember that? It'll change. Now it will become x bar minus k, and k we're going to get from what's called confidence interval. So this k sigma over square root of n, and k is the constant. It's a constant, and he has a table in the book where he has the values of k. I wish I had a little more time. So this is in the book. I'm not sure the page number. You see these values, q% value of k? Now, I'll show you how you can actually calculate that without these things. But if you wanted a 90% confidence interval, k would be 1.64, 95, 1.96. And he says if you basically have a large population of resistors, the real standard deviation is 4. Find the confidence intervals if you got a sample size of 100. So the key thing is K, if you want 95% confidence, K is 1.96. 1.96 times 4 divided by square root of 100 is 0.78. So you're going to go 0.78 above and below the mean. If the mean is going to be a value of 100, it goes from 99.22 to 100.78. What you're going to see in a second is, I will show you this, there's going to be some real tricks, and we have time for it here. But I'm going to give you some problems to do, and I'm going to ask you to please do these things, so next time when I start solving these and showing you the tricks, it won't be like just completely baffling. Good luck on your tests. I know you got that thing. And do these problems. 4-4.1 out to 4-4.3. And the answers, I think I've already provided some. Sorry I had to rush through that last part. How many have the ag tested? That explains, I guess, so focus on some others. But this is going to get better in a hurry.